Good evening, ladies and gentlemen. My name is Sugata Banerjee. I'm an assistant professor at Lake Forest College, Illinois, USA, and I wanted to be here in person to present our work, but unfortunately, due to visa issues, I couldn't make it. So, here's my presentation, and if you have any questions, you can mail it directly to one of us, and hopefully, we'll be able to answer it. The topic of our presentation here is evaluating predictive models for solar energy growth in the US states and identifying the key drivers. And this work has been done by Johin Chakraborty, who was a summer research student at our college, and myself. I am from the Department of Mathematics and Computer Science. So what is this research? Why did we do it? The total installed solar capacity in the world grew by about 200 times between 2000 and 2015. Now, this growth was not even across the states, across the US states, and we created a list of possible factors that could affect the growth of solar across the states, and then we tried modeling next year's solar growth from this year's data. So these are some of the candidate factors that we thought would be responsible for predicting the solar growth or affecting the solar growth. Some of these are pretty obvious, like solar potential of the state, which is based on geography and weather, then cost of solar installation and the population. But then there are some other factors which are not so obvious, like the ratio of Democratic to Republican voters, the percentage of people who have been to high school, or percent of people that are white or black or Hispanic or Asian. So we identified about a dozen data sets which contained an information about the 50 US states and DC, and the range of data that we could reliably find was for the years 1997 to the year 2014, and of these dozen data sets, we cleaned and gathered the data into our tables, and in some cases, like in the election data, the data was available with an interval of 4 years, so the intermediate years were interpolated from the existing data. A more detailed discussion about these data sets can be found in our paper, so if you need to know more about how we got the data, you have to read our paper. The potential, some of these data are visualized in the following slides. So the solar potential is, as you can see here, Arizona, California, Nevada, and New Mexico. This region gets a lot of sun, and the northern states like Wisconsin and Alaska, they get a lot less sun. So the solar index is low for the northern states. Then here's a map of the median household income. This is from the United States Census Bureau, and we use this data in our research. Then here's the map of the total population of the US by state, and then here's a breakdown of the population by white, African American, Asian, and Hispanic. So all of this data was used in this work. So how did we work with this data? We used regression techniques. Regression is also known as curve fitting, and a line or curve that best models the behavior of the data is calculated, is found, and used to predict unknown data points. We tested several types of regression: linear regression, polynomial regression, and ridge regression techniques, and we found none of these properly modeled the data. These were all unsatisfactory, and at best we could get only about 17% accuracy of the model. So that means approximately 17% of in 17% of the test cases our data could predict our model could predict the data accurately. Then here's a visualization of our regression results. If you look at the scatter chart on the left, you'll find that the purple dots represent the actual data that we tested, and the red line, the small red line, is our model. As you can see, the data points don't really follow a straight line or any kind of a curve, So whatever curve we fit onto that, it will not give us a good result. The figure on the right shows how the accuracy grows with as we increase the number of factors, and as you can see, we reach that 17% mark with only 7 factors. So these 7 are the largest, the most important factors for predicting the installation of solar. The other factors don't have that big an effect, although they do have a very slight effect. They don't have much effect. The second model that we tried was random forests. So random forests are an ensemble learning method popular for regression. This is a machine learning technique. So they operate by constructing a multitude of decision trees at training time and outputting the mean prediction of the individual trees. So you have these trees, decision trees, which predict a particular data value, and you have a bunch of random trees. That's why it's called a forest, and then you get a predicted value for each data point after training. So our random forest results were much better. In fact, they were pretty good. We used 75% of the data points for training and the remaining 25% for testing. For predicting this year's solar growth from the 22 independent variables, this model's efficacy or accuracy was 86%. For predicting the next year's solar growth from this year's growth, the model's efficacy was 90%, which is a pretty accurate model. Our random forest results also showed that all of the variables that we selected were not equally important in predicting the solar growth. For example, you can see the most important factor for predicting this year's solar growth is factor number 12, which is the cost of solar installation. The second most important is number 4, which is median household income. So if people are rich and the cost of solar installation is low, then people will buy more solar installation. Next year's solar growth depends very heavily on this year's solar growth. So this is the factor which most heavily influences next year's solar growth. The other factors which influence it somewhat highly are factor number 7, which is the percent of population with a high school degree or higher, and number 3, which is the total population. The second technique that we used is known as support vector regression. It's a machine learning technique, and in support vector machines, SVMs are supervised learning models. They are very popular in machine learning. They are associated with learning algorithms that can analyze data, and they're usually used for classification and regression analysis. So you give the system a set of training examples, and an SVM algorithm builds a model that assigns new examples to one category or another. A version of SVM for regression called a support vector regressor was proposed in 1996 by Vladimir Vapnik and co-researchers. So what an SVM does is it tries to find a curve that passes through the data points perfectly, and it does by so it regresses by trying to minimize the error between the prediction and the real data. So we fitted an SVM regressor model to all of the data and calculated the model residuals for each state for each training year. Then we averaged these residuals for each state over all the training years to find the mean residual for each state. So when we predicted the solar energy installation value for a state and we found the state did not achieve this value, we said the state has a negative bias. When we saw that a state's real value exceeds the prediction, we say the state has a positive bias. So we call this a statewise bias, and you can see this statewise bias in this figure. Here you can see the state with the highest positive bias is DC, which is not really a state, and then the second highest is Hawaii, and the state with the lowest bias, lowest negative or highest negative bias is California. So the way we interpret these biases is, if some state has a very high positive bias, that means that state has already exceeded the potential for that state. So it is unlikely that it will have tremendous growth in the coming years. On the other hand, a strong negative bias means the state has very ideal conditions for growth, but for some reason the state has not achieved its potential. So that state has a huge potential for growth, and we can concentrate efforts for increasing solar energy installations in that state. DC is a special state because it is very small. It is the smallest among all states, and it has it is completely urbanized. So that could be the reason why it has such a positive bias. Hawaii is an island state with no sources of conventional energy like coal or petroleum, and so conventional energy is costly. That could be one of the reasons why Hawaii has such high positive bias. California, on the other hand, could be much better. California has ideal conditions, and yet California has failed to achieve the solar installations that it could. That's why we say California has a negative bias. So here's a map, statewise visualization of the same thing, and you can see other states which have slightly positive bias are Nevada, Florida. So these states also have a good solar installation. And then we repeated the same experiment by year. So we fit an SVR to the data, and we found the mean residuals for each year average across all states, and we found the year-wise solar percent bias to follow a nearly monotonically increasing trend over the years. So which means the solar percent increased over the years, and every year the solar percent for every state was better than predicted, and this is likely due to some factors. So you can see the graph here, and this is probably due to some factors that we did not consider in our experiments, such as changing government policy or growing awareness about environment, reducing cost of solar installations, etc., etc. To conclude, we have tried to solve the unaddressed problem of predicting the solar energy production and predicting the next year's solar growth at a US state level, and we consolidated data from over a dozen different data sets to identify potential influencing factors. We identified a random forest regression model that can predict or explain the dependent variables with 90% accuracy, and we identified statewise biases using a support vector regressor, which can help us identify states with high or low potentials for growth. In future, we wish to analyze these biases to better understand their cause and improve our models further. So, if you have any questions, you can directly mail us the questions. Here are our email IDs. Thanks for listening.